My recording got cut off a little earlier, so I will continue with there are infinitely many primes proof. Before I actually get to the proof, I would like you to consider a numerical example, as that will be at the heart of the proof. Not this particular numerical example, but the way I go about constructing the number. So let me consider number 5. Let me consider number 5, n is equal to 5. What I will do is take all numbers up to 5 and multiply them together. So I'm creating a new number. Let me call that new number big N. And the way I'm going about creating this other new number big N that I'm calling is as follows. I'm going to take all integers up to 5, multiply them together. So 1 times 2 times 3 times 4 times 5. And I'm going to add 1 to it. 1 times 2 times 3 times 4 times 5, I think, is 720, if I calculated that correctly. So plus 1 is 721. Now, the number 721 is clearly greater than 5. So the question is, this number is either prime or a product of primes according to proposition 31 that we talked about a bit ago. So question is 721 prime or not? Well, I don't know, but by looking at it, so I really, just by looking at it, can't tell whether it's prime or not, but we can start dividing 729 by some numbers to see if anything goes into it. So notice the following. If you divide 721 by 2, you'll get a remainder of 1. So 2 cannot possibly be a factor of 729. What about 3? If you divide 721 by 3, you still will get a remainder of 1. So number 3 is also not a factor of 721. The same with 4. 721 divided by 4, remainder 1. 721 divided by 5, still remainder is 1. So all of these numbers from 1 to 5 certainly cannot possibly be factors of 721 because of this plus 1. Anytime you divide 721 by any of this, you'll get a remainder of 1. So no matter what the factors of 721 are, they have to be bigger than 5, because all numbers up to 5 don't even divide into 721 without a remainder. So if 721 is prime, that's fine, but if it isn't, whatever the prime factors of 721 are, they have to be bigger than 5. As it turns out, in fact, 721 is equal to 7 times 103, and both 7 and 103 are prime numbers. So this is the prime factorization of 721. Nothing particularly interesting about 721 or these numbers that I considered, but the way I am going about this particular numerical example actually explains a lot as to how we go about proving this theorem. So in general, to show that some quantity is infinite, or anything that has to do with infinity, generally speaking, is hard to prove. That's why I mentioned before that this theorem is one of the most beautiful ones, because it's a very simple, short, and very clever proof. So let me start with the proof. What would be the aim? Let's consider some arbitrary some arbitrary, it could be prime number. Prime number. When I say arbitrary here, it means that I have a choice to pick any prime number I like. If I can show that for any choice of this number, I can always come up with another prime that is larger than my chosen prime, then I'm showing that there are more primes than I think there are. In fact, there are infinitely many primes. Why infinitely many? Because my choice for this prime number was a very arbitrary one. So my choice for a prime could be different from yours. So no matter what the choice for this prime number is, if you can always come up with another prime larger than that, then we are showing that there are infinitely many primes. So that's the logic behind what we're trying to do here. So let me consider some arbitrary prime number n. Let me call that number n. Okay. Construct big number n, much like this example, to be the number 1 times 2 times 3 times 4 times absolutely all numbers up to n. Not only prime numbers up to n, but all numbers up to n. So here my choice was 5. So all I did is took all numbers up to 5, multiplied them together, and I added 1. I will do the same here. So no matter what my choice for this prime number is, I'm taking all the numbers before that, multiplying them together, and adding 1. So obviously, n is larger than my little number n, my prime n, by construction. I'm making sure that big N is much bigger than smaller n. Just like here, 721 is much larger than 5. So now this number n is either prime or a product of primes. That is by proposition 831 that I mentioned in the previous page. So let's consider the case when n is prime. If n is prime, we are done because we found a number bigger than little n and prime. And that is the aim. The aim is, no matter what my choice for little n is, I can always come up with some other number bigger than little n, and that being prime. So if this big N happened to be a prime, then I'm done. I described a prime number larger than my choice. What happens if n is not prime? Case when n is not prime. Okay, if n is not prime, then n must be a product of primes, again by proposition 31. N must be a product of primes. Say, I don't know what they are, maybe 2, maybe more than 2. A number doesn't have to have only 2 prime factors in its prime factorization. It could be more than 2, but for sake of argument, let's just say that n is equal to big A times big B, where A and B are primes. So I'm going to talk about A. Talking about A is the same as talking about B. It doesn't really matter, or both at the same time. Now, could A be bigger or larger than my little n? Well, for A to be larger than the little n, A cannot possibly be 2, cannot be 3, cannot be 4, cannot be 5, cannot be any of the numbers up to n. Why? Well, because if A is a factor of n, anytime you divide n by A, you should have no remainder. But if you divide n by anything that's less than n or less than n, meaning if you divide n by 2, by 3, by 4, by 5, and so on, up to and including n, anytime we do so, we will get remainder 1. So no matter what A is, and I don't really care what A is, I just know that A is prime and it cannot be anything less than or equal to n. Then I'm basically done. So let me just write this down. So in a nutshell, this is the proof with a particular example. Obviously, you cannot prove a theorem with one numerical example. I just wrote that numerical example so you get the idea or the flavor of the proof. So could A be larger than my little n? No. The answer is no. If A is less than n, then, well, not then. If A is less than n and a factor of n, then A must divide n evenly. But that is not the case. That cannot be the case. Because none of the numbers up to and including little n divide n. There is always remainder 1. So hence A must be larger, A less than or equal to n. Hence A must be larger than n. So we have a prime number that is larger than n. Since the choice for little n was arbitrary, Then, given any prime number, we can always find another prime larger than that. Larger than that. Hence, there must be infinitely many primes. There must be infinitely many primes. Well, that is actually the end of lecture 4. Next lecture, I'll be talking about Platonic solids, which concern the very last book of Elements, but that will be the content of the next lecture. Surely, with this lecture, I will post some problems that are related to this concept that you should look at. So long, everyone. Until next time.